The performance curve of a flat plate collector, it's so-called the ID of the solar thermal collector. On the Y graph axis, we can see the efficiency in percentage, and on the X graph axis, we can see the difference of temperature between the ambient temperature and the collector average temperature in the fluid inside. And if this delta T is smaller, we have higher efficiency. When this delta T is high, then we have a lower efficiency. The biggest efficiency on a solar thermal collector is the so-called optical efficiency. So we just have optical losses, we don't have thermal losses in that point. And on the other side of the curve, we have the so-called stagnation temperature. It's the temperature when we stop to operate our collector because we cannot extract any more energy from it. In any point of this curve, we have the so-called operating point, which varies depending on this delta T, the temperature inside of the fluid of the collector and the ambient temperature. If we draw a line from the optical efficiency, everything above this line is the so-called optical losses, and below this line and above the ID performance curve are the heat losses. On a certain operating point, we have both optical and heat losses, and this gives then the output of a collector at any given time. So in green, you can see the useful heat area, which is the amount of heat that you can extract from one collector. If we take an example, let's say 70 degrees being the difference of temperature between the ambient temperature and the collector temperature. We have this operating point, and for this case, we have 20% optical losses, 30% heat losses, and 50% useful heat, which means that at this operating point, the collector is being operated with an efficiency of 50%. Here we can see typical performance curves of different collector types. We start with an evacuated tube collector, then a flat plate collector, followed by an air collector, and finally a plastic absorber collector without glazing, so it has huge thermal losses, and that's why the curve is so sharp. All in all, this is the power curve of a solar thermal collector, which can be defined by the power being the optical efficiency multiplied by the irradiance on a certain plane where the collector is located. And then I have all the losses with different coefficients of different magnitude multiplied by the delta T depending on the operating temperature and the ambient temperature. Additionally, solar collectors can be tested. There are different norms. For photovoltaics, the two most important ones are the EIC 61215 and the EIC 61730. These are broad accepted standards in the industry. Moreover, for solar thermal, there is a so-called solar key mark testing system with a certification body responsible to test and certify solar thermal collectors. The testing of the collectors is mainly using one of two methods: the steady state, with a certain number of days above a certain solar radiation necessary to test the collector, and a quasi-dynamic method, which allows collectors to be tested also in climates with much more clouds and less sunny days. In all these methods, we have the defined standard testing conditions, STC, which imply 1000 watts per square meter solar radiation, 25 degrees Celsius air temperature, and an air mass coefficient of 1.5.